Hello. In this video, we're going to be discussing double integrals over general regions. Last section, we found the volume under a surface over a rectangular region. Now what we're going to do is extend that idea to more general domains. The basic theoretical procedure for this is quite simple, and it's based on our knowledge of how we integrate rectangular regions. If the region is rectangular in shape, we know how to set up the Riemann sum, so we do that with one added bit. We construct a new function, capital F, using lowercase f, the function that we want to integrate, and 0. What we do is we take our more general looking region D and trap it inside of a rectangle. In the rectangular part that's not D, we set the function equal to 0, and inside we set our new function capital F equal to lowercase f. All this means is that we don't need any new theory to integrate over a general region. We just use what we know about rectangular region integration. If we look at this picture with an actual surface over the region that we want to integrate, we see that whether or not our added rectangle is present, the actual surface that we're integrating doesn't change, because out here everything is equal to 0 and doesn't contribute to the total volume. To mechanically work out these problems, what we want to do is we want to take these more general looking regions, I have a couple examples here on the bottom of the slide, and figure out how to represent them in a way that allows us to write down an integral that we can actually compute. Our method of attack here is going to be to classify these as one of two types of regions for integration. In the example on the left, we see that the top and bottom parts of this region can be described in terms of continuous functions of x. And the left and right sides are just vertical lines. Likewise, we can look at what's going on for the type 2 regions, and we see that the left and right boundaries are continuous curves, and the top and bottom are straight lines. So we look to classify our more general regions as one of these two types as possible, and it turns out that it's not going to be difficult to write down the iterated integral in these cases. Here are some more examples of type 1 regions. This is the example from the previous slide. We see that we have the continuous curve on the top and the bottom here. For this example, we can imagine there being continuous functions of x if we split it in half and look at those two pieces as being our continuous curves. And then for the final example here, we see that those are our two continuous curves defining the top and bottom regions, and our left and right endpoints for the x direction are just given by those values. Type 2 regions work similarly, except it's the left and right hand sides where we want our continuous curves. And we can see our pieces for the left and right boundary defined like this. Now, sometimes it happens that our regions do not fall into either the type 1 or type 2 category. If we look at this example D here, kind of a lopsided heart shape, there isn't a clear distinction between what would be a continuous function for the top or a continuous function for the bottom or the left and right sides, as we saw clearly for our previous type 1 and type 2 examples. However, if we look at this right-hand picture with this vertical line drawn here, we can see pretty clearly that D1, the left half, is a type 1 region, and D2 also is a type 1 region. So we can split these more difficult general regions into two halves, and then after we have split it into those two halves, we just say that the integral over D is equal to the integral over D1 plus the integral over D2. All right, thank you so much for listening, and in subsequent videos we will be doing more examples to show how this works in practice.